Yeah, they keep on being like, hello, I want you to come here, spend your money here.
Alright, first, real quick, are there questions on the multiple choice questions from last night?
I kind of have one. I kind of understand it, I kind of don't.
I wish they had numbers.
Yeah.
I didn't spend time formatting it, just threw them all in there.
It's the.
I was the one that, wait. No, I don't need to do this one.
Because you're like, because of the derivative, yada yada, and I'm like, what?
The average is like 1
Yeah, the one on top of the table.
Okay. So, this one right here, we're told that the point 0, -5 is on the graph, right? So we're at 0, -5 right here. And we are told that the slope is less than or equal to 3 everywhere. So the maximum the slope could be is 3. So if we think about, well, if I go up 3 over 1, up 3 over 1, the highest point that I could possibly be at x equals 2 is 1. Right? I can't be any higher than that if the slope is less than or equal to 3. I could be way lower than that, right? The slope could be -7,000. So I could be way down here, but the highest that I could be if the slope is less than or equal to 3, if I go up 3 over 1, up 3 over 1, the maximum y value I could attain is 1. So 2 is why I can't get to 2.
That makes a lot of sense now. Okay.
There's one somewhere that I still don't understand. What about the one before that?
Right before this one?
Oh yeah, I just didn't know how to separate them. But don't you just do
Product rule. You mean?
Okay, never mind.
That works.
Okay, the one below that then, because like
The table one?
no, the one below the table. Yeah,
Oh, that one.
that one.
This
Yeah.
one?
Because like I didn't think it was that hard, and then I put the answer all practical. Because can you just do like if you're can't x squared plus 1, but you don't have one that could be
If you're adding two things inside of a square root, you cannot take the square root of each piece separately. Any others? What?
I have like a bunch of things starred, but I went over them and I wrote on the ones that what I messed up on. Like I know.
Well, if you come up with questions later, you can always ask later. So nothing else on these? So, I mean, how are we feeling so far after limits and continuity and derivative rules? Easy?
Sure. Can I ask you another question? You're taking the normal derivative, you just bring the one out front and then subtract one from that.
Yeah.
If
For
you have x
power
squared,
rule?
so like if you had x squared, I could not figure out the whole length. I can't figure the anti-derivative stuff. I keep the anti-derivative. Do you have a stapler?
I do have a stapler, yes.
Why is only one control?
Does have to show less.
I didn't pay attention to it last time.
The copier has decided to randomly hole punch papers instead of hole punching all of them.
I don't think. And I see it still doesn't want to do back and front.
Okay, well, that part was my fault.
Yeah. Okay.
Alright, today we're going to look at applications of derivatives. So most of this is mins, maxes, increasing, decreasing, concavity, that type of stuff. So first, to find local mins and maxes, find the derivative, set the derivative equal to 0, solve for your x values, and also look for where the derivative is undefined. Okay, so points where the derivative equals 0 and where it's undefined are your critical points. Then we want to put points, all critical points, on a sign chart. Plug a value in between each of our critical points into the derivative and get the sign, positive or negative. If our derivative changes from negative to positive at a critical point, it's a min. If it changes from positive to negative at a critical point, it's a max. We also say that f is increasing on the intervals where the derivative is positive, and f is decreasing on the intervals where the derivative is negative. Right? So let's go through a simple example here. So for this function, x cubed plus 3x squared minus 9x minus 4, we want to find all local mins and maxes, and then state where the original function is increasing and decreasing. So first step would be to find the derivative. Okay, so derivative would be 3x squared plus 6x minus 9. So set that derivative equal to 0 now. And I can divide out a 3. That should make this a lot easier. Right? And I would just get x squared plus 2x minus 3. Then I think this one factors.
What?
Right. So we're looking for two numbers that multiply to negative 3 that add to positive 2. So we would have x plus 3 and x minus 1, which means our solutions are negative 3 and positive 1. So that's where the derivative equals 0. We also would want to check for any places where the derivative is undefined. Right, there aren't any in this case. So these are all of our critical points. Put those on a sign chart. Always label your sign chart. Right? So here we care about the first derivative sign chart. And then plug a value on each of these intervals into the derivative. So you can plug negative 4 in, and usually it's easier if you have a factored form or a simplified form to plug it into that version. Right? So if I plug negative 4 in, this would be a negative times a negative. It would be positive. If I plug a value in between negative 3 and 1, 0 would probably be a good choice. This would be a positive. This would be a negative. So positive times a negative is negative. And a value greater than 1, this would be positive times positive, be positive. So now let's interpret this sign chart. At negative 3, if I'm changing from a positive slope to a negative slope, positive slope to a negative slope means that would be a local max. Okay, so local max at x equals negative 3. If I'm changing from a negative slope to a positive slope, that's a local min. So local min at x equals 1. Then we also want to describe intervals for increasing and decreasing. So we can say f is increasing on these two intervals, right? So negative infinity to negative 3 and 1 to infinity, and f of x is decreasing on the interval negative 3 to 1. Now, a lot of times, if these types of questions show up on the free response, they ask you to justify your answer. And so we would need to explain each of these with a sentence or a half sentence. So, for example, for the first one, how do I know that I have a local max at x equals negative 3? How would I put that into words?
The slope of f of x is increasing until negative 3 and then is decreasing after negative 3.
Yeah. Okay. We could also say f prime changes from positive to negative, right? So yeah, either of those would be perfectly acceptable explanations. So I'm not going to write out all the explanations for these, but we need to be comfortable writing out a sentence to explain that word. Okay? Feel okay with those? All right. Then the next idea was absolute mins and maxes. Okay, this is similar to local mins and maxes, but if we're talking about absolute mins and maxes, usually we will be given an interval. Okay, so for example, in this problem right here, it's the same equation as the last example, but now it says find the absolute mins and maxes on the interval negative 4 to 4. So the only difference between absolute mins and maxes and local mins and maxes is these could occur at an endpoint. So what I want to do is find all critical points, just like we would for local mins and maxes, and then take my critical points and the endpoints and plug those into the original function. Okay. So we've already found the critical points, right? Our negative 3 and positive 1. And then my endpoints are negative 4 and 4. So I'm going to plug all 4 of those values into the original function. So I want to evaluate f of negative 4, f of negative 3, f of 1, and f of 4. These are the only possible places where an absolute min or max could occur, either at a critical point or an endpoint. So I just need to test these 4 options. Whichever one gives me the greatest value is the absolute max. Whichever one gives me the smallest value is the absolute min. So for time's sake, these work out to be 16, 23, negative 9, and 72.
Oh, it goes back into the original concept.
Right, into the original function. Right? So what this means is my absolute min occurs at x equals 1. The absolute min is negative 9. Right? I think I messed up and put this in the wrong spot. I think I put it on the next under concavity. Put this. So make a little note. Where does something happen means x value. What means the y value. Like, where does the min occur means find the x value. What is the min means find the y value. And yes, I remember. Yeah, like she wrote the correct information on the top of her test so she wouldn't forget, and then messed it up
And
when
then
it was
you took
actually
an arrow,
asked.
because it was on the second page I just had a row number, took an arrow, wrote it all the way to the top of the page, and then wrote the gap.
Alright, so to interpret this, we would say the absolute min occurs at x equals 1, the absolute min is negative 9. So we could just write out the entire coordinate point. We could say that's at 1, negative 9, and the absolute max occurs at 472. Questions on mins and maxes? All right, then the next thing is concavity. So concavity comes from the second derivative. So to find concavity, we just take the second derivative. Find all points where the second derivative equals 0 or is undefined. Put those on a sign chart. All right? So let's take this same function that we used in the first two examples. But now we want to find the second derivative. So we know the first derivative is 3x squared plus 6x minus 9. So the second derivative then is going to be 6x plus 6. Set this equal to 0. And I think we get negative 1. So only one possible point of inflection. Remember, these are called points of inflection. We set the second derivative equal to 0. We don't know for sure if it is yet. So let's put it on the sign chart. And plug a value on either side of negative 1 into the second derivative. So if I take negative 2 and plug it in here, I would get a negative value. If I plug value greater than negative 1, say 0 in, I would get a positive value. So since I change sign, that means negative 1 is a point of inflection. Okay. Then, if I want to write the intervals of concavity, I would say f of x is concave down on the interval negative infinity to negative 1. Concave up on the interval negative 1 to infinity. We okay with that? All right. Then we brought all this stuff together and looked at connecting graphs. Okay? This is a pretty popular type of question on the AP test. Okay? And more often than not, you are given a graph of the first derivative and asked questions about the original function. Every once in a while, they'll throw one on there where they give you the graph of the second derivative. So you do have to pay attention. But the majority of the time, you're given the first derivative. Okay? So, and we'll look at more of these next week when we talk about free response, okay? But thought it was important enough to look at one today as well. So we're given a graph of the derivative, and we are told that f prime has horizontal tangents at negative 1, 1, and 3. And then we're also given information about the areas of those pieces, which we would only need for part D here. So A says find the x-coordinates at which the original function has a relative maximum. Okay, well, to do that, we want to kind of go through the same process that we did when we were just given a function. Okay? We want to make a sign chart. So I want to think about where does the first derivative equal 0? Those are the points that go on my first derivative sign chart. Well, we would still technically count 1 and 4, but to answer the question, then you're right. It will only happen at negative 2. So if we fill out this sign chart, we're thinking about the sign of the function, right? So I'm just looking at whether it's positive or negative, not the slope. So to the left of negative 2, the function's positive. here it's negative, and in between here it's also negative. So we are only looking for relative maximums. That's where the slope changes from positive to negative. So that will only occur at -2. And it does say give a reason for your answer. So we would say that x equals -2 because f prime changes from positive to negative at this value. Part B then says, well, where is the original function both concave down and decreasing? Okay, well, we already found where it's decreasing, right? From our first derivative sign chart, it's decreasing here and here. But to figure out concavity, we need a second derivative sign chart. So, if I have the graph of the first derivative, how can I figure out where the second derivative is equal to 0? Right, where it changes slope, or where the slope is equal to 0, which would be at -1, 1, and 3. So those would be the zeros for my second derivative. 1, 3. Let's fill out this sign chart. So now I'm looking at the slope of the first derivative. So to the left of -1, the slope is negative. Between -1 and 1 is positive. Between 1 and 3 negative, 3 to 4, it's positive. So looking at these two sign charts, I want to figure out where the original function is both concave down and decreasing. So I'm basically just looking for an overlap of negative signs on these two sign charts. Yeah, I think it'll be -2 to -1, and then 1 to 3. And again, it says give a reason for your answer. So we could say something like, on these two intervals, both the first and second derivative of f are negative. Okay, something like that. Then part C, kind of already did all the work for that in part B. It just says find the x-coordinates of all points of inflection. Well, points of inflection are where the second derivative changes sign. So just looking at the sign chart we already created, well, that happens at -1, 1, and 3. Okay. And again, the reason for your answer, you'd say f prime, the slope of f prime changes sign, or we could say f double prime changes sign. Okay. So part D actually goes into integrals then. So I think we're okay on time. We can do part D real quick here. It says, given that f of 1 equals 3, write an expression for f of x that involves an integral. So we want to think about the fundamental theorem of calculus for this, right? If we're talking about area under a curve, we want to use the fundamental theorem of calculus. So, I know an x value, and I know that f of 1 is equal to 3. So one of my x values, or one of my bounds, is going to be 1. I don't know the other one, right? It says write an expression for f of x. Okay, we're not finding a specific value yet. We want to leave this in terms of x. So my other bound would be x in this case. So I want to integrate the derivative. So this would just be f of x minus f of 1, the antiderivative of the top bound minus the antiderivative of the bottom bound. And then it says, write the expression for f of x. So I would just want to solve this for f of x and add that f of 1 over. So we can say f of 1 plus the integral from 1 to x of f prime of t dt equals f of x. What's up?
So, why are we doing?
Oh, okay. And then
So now it says take this and find f of 4 and f of negative 2. So first, I just want to plug 4 in for x. Right? So I can say f of 1 plus the integral from 1 to 4 of f prime of t dt equals f of 4. So we know f of 1 is equal to 3. Right? So this piece is just 3. Then this says, what's the area under f prime from 1 to 4? Okay, well, we're given that information, right? We're told that these areas here are 9 from negative 1 or negative 2 to 1. So this area would be negative 9 since it's below the x-axis. And then this area we're told is 12. But again, since it's below the x-axis, it would be negative 12. So this piece, the area from 1 to 4 is negative 12. So f of 4 is negative 9. Similarly, if I want to find f of negative 2, I would say f of 1 plus the integral from 1 to negative 2 of f prime of t dt equals f of negative 2. So again, we know f of 1 is 3. We know that this area is negative 9. But I'm going backwards. If I'm starting on the right and going to the left, and I'm starting at 1 and going to negative 2, we would have to make that negative again. So this would actually be a double negative, which means 3 minus negative 9 is 12. Okay, so part D was a little bit tricky there. Okay, I think A through C were fairly straightforward, and those are what we are talking about here. Part D was a little extension with integrals. Questions? All right, then other applications of derivatives. Let's look at a couple related rates problems. So related rates are just an application of implicit differentiation. First thing we always want to do with related rates is draw a picture. Right? Draw a picture and label the situation. Then we need to write an equation that connects all of the variables and the unknowns in the problem. Then implicitly differentiate every variable with respect to t. So that means every time I take the derivative of a variable, I tack on a d whatever dt. Then I plug in everything that I know, and I should only have one unknown to solve for. So let's go through a couple of examples here. So first, an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. The distance between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when that distance is 10 kilometers. What's the horizontal speed of the plane? So we're saying we've got some radar station here. Here's my plane flying this direction, right? Flying towards the radar station. We know that that height that the plane is above the ground is constant, right? It's staying this high above the ground. But then this distance between the plane and the radar station is decreasing, obviously, since the plane's going in this direction. So we're given, or we're told that this variable is s, the distance between the plane and the radar station. Okay, then we can label the other sides however we want. Okay, we can call it x and y, or a and b, or whatever we want. I'll call it x and y. So this situation can be modeled using a right triangle. Okay? So I'm going to have 6 different things, right? X, y, and s, and then dx dt, dy dt, and ds dt. So just list those out here. X, y, s, dx dt, y dt, and ds dt. So let's see what we know. So we know the plane stays at a constant height of 6 kilometers. So that would be this distance, right? This height. So we could say y is 6. I know that the distance between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour. So the distance between the plane and the radar station, that would be this distance, right? That rate is negative 400. So we would say ds dt is negative 400. And then we're also told at this instance, s is 10. Well, I only have 3 of the 6 things filled in. Okay? I need 5 of them filled in to solve for one remaining, right? So what we're trying to figure out is the horizontal speed of the plane. Well, the horizontal speed of the plane would be the rate at which x is changing, right? So that's what we eventually want to solve. So I need to figure out x and dy dt before I can do this problem. So, thoughts? So yeah, if I know 2 sides of a right triangle, I can use the Pythagorean theorem to solve for the third. Right? So we could say 6 squared plus x squared equals 10 squared. So 36, subtract that over from 100, get x squared equals 64. So x equals 8. Okay, what about dy dt? It's not changing, right? Its height is remaining constant. So dy dt is 0. Now we can set up our equation, which we already said was just Pythagorean theorem, right? So x squared plus y squared equals s squared. Take the derivative of this and implicitly differentiate each variable. So the derivative of x squared would be 2x dx dt, then 2y dy dt equals 2s ds dt. And now I can plug everything in and solve for dx dt. So I'll have 2 times 8 times dx dt plus 2 times 6 times 0 equals 2 times 10 times negative 400. So we get 16 dx dt equals negative 8,000. So divide both sides by 16. Get dx dt equals negative 500. And then my units would be questions on that one? I was going to say, I know that we struggled with related rates. Was your favorite? All right, let's do one more related rates problem then. Okay, we've got a conical cup that's 4 centimeters across, 6 centimeters deep. So before we go any further, let's sketch that out. So I've got a cone that is 4 centimeters across and 6 centimeters deep. So 4 centimeters across would be the entire diameter, right? So let's say that the radius is 2. Now, we generally on a problem like this, you would be given the volume formula. So volume of a cone is 1/3 pi r squared h. So let's look at the rest of the problem then. It says water leaks out of the bottom at a rate of 2 cubic centimeters per second. We want to figure out how fast the water level is dropping when the height of the water is 3 centimeters. So we are only given information about the height, okay, and asked about dH dt. Okay? How fast is the water level dropping would be dH dt. And then we're given the height at this instance. We're not given any information about R or dr dt. So what that tells me is I want to rewrite my volume formula only in terms of H. To do that, okay, we could use similar triangles. Okay, so if I think about a triangle with H and R, I can set up a proportion here. Okay, so I could say H over R equals 6/2. You can cross multiply and get 2H equals 6R. So if I want to rewrite this in terms of H, which variable do I need to solve for here?
No, R.
R. And I want to solve for R and then replace R in this equation. So if I divide 6 over it, I would get 2H over 6, or I could just reduce that to H over 3. So I can then plug this into my volume formula here. Say this is 1/3 times pi times H over 3 squared times H. Then we can do a little bit of simplifying here to make this a little easier. So if I square this, I would have H squared over 9 times H. And then I could multiply my 1/3 and my 1/9, get 1/27 pi, and then multiply the H squared and the H together to get H cubed. So we've changed our volume formula just in terms of one variable now. I can take that derivative and plug in things that I know. Okay, so I guess let's list out the things we know first. So water leaks out the bottom at a rate of 2 cubic centimeters per second. That would be the rate at which the volume is changing. Right? And if it's leaking out, that would be a negative value. Then we also know that at this instance, the height is 3. And we want to solve for dH dt. So I want to take this volume formula and find the derivative. So I would have dV dt equals, I would bring that 3 down, so 3 over 27 would just be 1/9. So I would end up with 1/9 pi H squared dH dt. Then I can plug in the two things that I know and solve for dH dt. So go ahead and do that real quick. So, 2 So I think we should get -2 over pi. And then my units would be centimeters per second if we're talking about the rate at which the height is changing. Feel okay on something like that?
Yeah, triangle. Like that's the part. I understand the related rate part. It's just like
So,
getting past that first step.
well, I mean, on a problem like this, usually they at least give you a point for like implicitly differentiating. So even if you had like the wrong equation, or even if you just differentiated this and correctly implicitly differentiated it, you would still get at least 1 point. Right? So I mean, if on something like this, if you don't know or don't remember to do this, at least try something. Right? Try to differentiate this formula. Okay? Try something. Okay? This test is all about just collecting as many points as you can. Okay? It's not necessarily about getting all the right answers. It's just about trying to do as much correct work as you can. Okay? Don't get super frustrated if you don't get all the answers. Just try to collect as many points as you can. All right? Final idea on this sheet is just a little bit about particle motion. We'll do a lot more with particle motion when we look at the integral stuff. Okay, but just with the derivative stuff, we talked about the basic idea of we've got a position function, its derivative is velocity, and then the derivative of velocity is acceleration. And then one of the big things that we looked at was at rest means that velocity is equal to 0. Right? It means the particle isn't moving, therefore the velocity is 0. So, quick example here. We've got a particle moving along the x-axis, and we are given a position function. We want to figure out where the particle is at rest. So, at rest means velocity equals 0. If I'm given position, I would want to find the derivative to get velocity. So, I think it actually makes sense to multiply this one out. So if I multiply this out, I would get t squared minus bt minus at plus ab. Okay. Now, to take the derivative, okay, I can just look at each piece. We could have taken the derivative in this form, but we would have had to use product. So, I think it's easier to just multiply it out first. So this would just be 2t minus b minus a. So now I want to set velocity equal to 0. So I can say 0 equals 2t minus b minus a. So if my goal is to solve for t, okay, and a and b are just numbers, so I can add both of those over to the other side. A plus b equals 2t. Divide by 2. We get a plus b over 2 equals t. Questions? I know we're going really fast this week, okay? Going through a lot of review material, and I'm just doing a lot of talking. Okay? So if you have questions, make sure that you stop me and ask me. Send me questions when you're working on these multiple choice problems in the evening. I want you to do that. I want to answer questions.